Hello there, and welcome to the Sleepy Nature channel. Here is something that will stay with you. Right now, at this very moment, certain mountains in the world are making their own clouds from nothing but air and patience. They are pulling invisible moisture out of the wind, lifting it gently into the cold, and breathing it out as soft white cloud that has never existed before and will never exist again in quite that shape. Mountains do not just sit inside the weather, they make it. They are weather engines, ancient and silent, shaping the rain and the wind and the snow of entire regions simply by standing still. Tonight, we are going to drift into that world together, into the high, quiet places where stone meets sky, and something as simple as the shape of a hill determines where the rivers run, where the forests grow, and where the deserts begin. Take a breath in, let it go slowly. There is nowhere to be but here. Let your body settle. Let your thoughts soften. The mountain is patient, and tonight, so are you. Imagine standing at the base of a mountain, not climbing it, not preparing to climb it, just standing at its feet with your hands open and your face turned upward. The first thing you notice is the air. It is different here. Even at the lowest slopes, where the ground is still flat and the path has not yet begun to rise, the air feels different from the air of the town you came from. It moves differently. It comes from a slightly different direction, and it carries something. A coolness, a freshness, a faint trace of stone and pine and distance that tells you something large is nearby. The mountain announces itself through the air before it announces itself through the eyes. You feel it before you fully see it, the way you feel the presence of the ocean before you see the water, through a quality of light, a shift in the breeze, a particular smell that does not belong to anywhere else. This is the first thing to understand about mountains and weather. The mountain is always doing something to the air around it, even at its base, even far from its summit. The influence of a high peak extends outward in all directions, and the air that reaches you as you stand at its foot has already been changed by its nearness to stone. The mountain you are standing beneath has been here for millions of years. It was lifted by the slow collision of two vast plates of rock, a process so gradual that no single moment of it was dramatic. And yet, the result is this: a wall of stone rising thousands of meters into the sky, altering the atmosphere for hundreds of kilometers in every direction. The forces that built it are the same forces that make the weather it creates. Pressure, movement, the endless restlessness of the earth beneath the surface. You are standing on something that is still, in the most technical sense, moving, rising or settling by millimeters per year, breathing in its own geological timescale. If you stood here for 100 million years, the mountain would rise and erode and rise again. But you are here for one quiet evening, and that is more than enough. Now, the air begins to move more purposefully. A steady wind arrives from the west, from across a great ocean, carrying the moisture it has gathered over thousands of kilometers of open water. You feel it on your left cheek, warm and damp and persistent. This wind has been blowing without interruption since it left the water's surface, and it has arrived here at the foot of this mountain because the mountain is in its way. The wind cannot go through the mountain. It cannot go under it. It must go up. And so it does, slowly, invisibly, beginning the great climb that will change it completely. The air that is moving past your cheek right now will, within a few hours, be a cloud somewhere above you. It will have given up its warmth. It will have given up its moisture. It will be something entirely different from what it is now. And the mountain will have made it so. And the mountain will have been entirely still while doing it. There is something deeply calming about this, the way transformation can happen through stillness, the way the largest things do not need to move to change everything around them. As the wind begins its ascent, it carries with it not just moisture, but also the most extraordinary collection of invisible passengers. A cubic meter of air anywhere on Earth contains thousands of tiny particles too small to see with the naked eye. Particles of sea salt that have been thrown up from ocean waves and carried inland by the wind. Particles of soil from distant deserts lifted by dust storms months ago and transported halfway around the planet. Particles of pollen from flowers that bloomed and faded on another continent entirely. The microscopic remains of living things, fungi and bacteria, floating on the air currents like seeds. All of these invisible travelers are rising with the wind as it climbs the mountain's face, and they matter enormously, because without them, there would be no cloud. A cloud is not simply moisture, it is moisture gathered around something. Each water droplet in a cloud forms around a tiny particle, using it as a nucleus, a seed, a point of beginning. Without these microscopic passengers, the moisture in the rising air would remain invisible and uncollected. With them, it becomes cloud. The mountain's weather begins, in a very real sense, with dust from a desert, with salt from an ocean, with pollen from a flower on the other side of the world. Everything is connected, and the mountain is the place where the connection becomes visible. There is a specific altitude on every mountain. It changes with the seasons and the temperature and the humidity of the arriving air, at which the invisible becomes visible. Below this line, the moisture is held in the air as vapor, unseen, unfelt, except as a certain quality of dampness. Above this line, the vapor condenses into droplets, and the cloud begins. Meteorologists call this the lifted condensation level, and it is the mountain's first act of weather creation. If you were to watch a hillside carefully on a humid morning, you might actually see this line. The cloud forms at a particular height and no lower, as if drawn by an invisible rule. Below it, clear air. Above it, white mist, building. The line is not perfectly sharp, but it is real, and it is caused entirely by the temperature of the air at that altitude. The point at which the air has cooled enough through its long climb that it can no longer hold its moisture invisibly. The mountain has cooled the air by the simple act of making it rise, and the result is cloud. On the windward slope, the side of the mountain facing the arriving wind, the clouds build through the morning hours with a slow and patient inevitability. You can watch this process if you find a comfortable place to sit on a warm hillside. In the early morning, the sky above the mountain is clear. By mid-morning, small white puffs appear at the condensation level and drift slowly upward. By noon, they have grown into substantial clouds, wider, taller, their bases flat where they formed, and their tops rounded and billowing where the rising air is still pushing them upward. By afternoon, on a warm, humid day, they may have grown into something enormous and magnificent, great towers of white and gray that cast moving shadows on the slope below and occasionally produce a rumble of distant thunder. All of this from a wind and a mountain and nothing more. All of this from the simple fact of air being lifted and cooled and allowed to release what it carries. If you feel like leaving a comment below, even just a word about how you're feeling right now, we'd love to hear from you. This channel grows through your kindness. The rain that falls on the windward slope of a mountain is often called orographic rain, rain caused by the shape of the land. It is not the only kind of rain, but on many mountain ranges, it is by far the most reliable. The windward slopes of the great mountain ranges receive rainfall that the surrounding lowlands could only dream of. The western slopes of the Cascades in North America receive 4 or 5 times more rain than the eastern side. The windward face of the Western Ghats in India receives rainfall so intense during the monsoon that it is measured not in millimeters, but in meters, several meters of rain in a single season. The mountain does not produce this rain from nowhere. It takes the moisture that the wind has gathered over ocean and plains and delivers it to the slope in concentrated, reliable abundance. The mountain is a collector and a giver. It concentrates what is diffuse and delivers it where it is needed, or at least where it arrives, and where life has learned over millions of years to expect it. The sound of rain on a mountain slope is different from the sound of rain in a city or a flat field. It comes in waves, following the contours of the hillside, each wave producing its own particular sound as it moves through different types of vegetation. Rain through high pine forest sounds like static, a uniform, continuous hiss that fills the air and makes all other sounds seem distant. Rain through broadleaf forest is more varied. Larger drops falling from wider leaves produce individual sounds, a kind of irregular drumming that is never quite predictable. Rain on open rock produces a clean, sharp percussion, each drop a distinct event. And rain on deep grass is softer than all of these. A whisper, a sigh, the sound of something very gentle touching something very patient. All of these sounds are happening simultaneously on a rainy mountain, layered one over the other, and the combined effect is one of the most peaceful soundscapes that exists in nature. It covers everything. It fills all the quiet spaces. It gives the mind something to rest against, a continuous and unhurried sound that asks nothing of you and offers everything. Let your breath be slow and easy. There is no need to follow every word. Let the mountain hold the story, and let the story hold you. The water that falls on a mountain slope does not simply run away. It does several things simultaneously, and each of them is important. Some of it is caught immediately by leaves and needles and mosses, which hold it briefly before releasing it as drips, slower, gentler, arriving at the ground minutes or hours after the rain has passed. Some of it soaks into the soil, where it may travel for weeks or months through the dark, cool underground before emerging as a spring on a lower slope, or feeding the roots of trees, or joining a stream far from where it fell. Some of it runs along the surface in thin films, gathering into rivulets, into streams, into rivers. But all of it, in its own time, finds its way downward. A mountain collects rain and snow melt the way a cupped hand collects water, holding it for a while, then releasing it slowly and steadily. The rivers that flow from mountains are therefore more reliable than rivers fed only by direct rainfall. They run even in dry seasons because they are being fed by water that was stored months ago in soil and rock and snowpack. The mountain is a reservoir, patient and deep, releasing what it holds at the pace the landscape needs. At night, the mountain's weather-making takes on a different character. As the sun sets and the rock cools, the air nearest the surface cools with it. This cool air, being denser than the warm air above, flows downhill, slowly, gently, following the paths of valleys and gullies toward the lower ground. This nightly drainage of cold air from the heights is called katabatic flow, and it is one of the most reliable and gentle of all mountain weather phenomena. If you were to sit very still on a mountain slope after sunset, you would feel it as a light, steady, slightly cool breath moving past your ankles, flowing downhill the way water flows, but more slowly, more quietly, without sound. It pools in the valleys below, collecting there through the night, making the valley floor noticeably colder than the hillsides. Frost forms first in the valleys, where the cold air drains and settles. The flowers on the valley floor bloom later in spring than the flowers on the slopes, because the cold arrives there last in autumn and stays longest in spring. The mountain organizes the cold as deliberately as it organizes the rain, not through intention, but through the simple physics of air and temperature and the pull of gravity on everything. This is only the beginning of the mountain's story, and there is so much more to settle into as the night grows quieter around you. There is a word for the side of a mountain that faces the arriving wind, windward. And there is a word for the side that faces away, leeward. These two words describe two completely different worlds, and on many mountain ranges you can walk from one world into the other in the space of a single morning. On the windward side, the world is wet. The trees are tall and dark and draped in moss. The ground is soft underfoot, always slightly damp even in summer, and the streams run full and clear year-round. The light comes through the canopy in soft, diffuse beams, filtered through cloud and leaf and mist, and it has a quality that is hard to describe, a greenish underwater gentleness that makes everything look as if it is being seen through very clean glass. The air smells of wet bark and decomposing leaves, and the particular clean mineral scent of moving water over stone. Everything on the windward side is a little softer, a little more rounded, a little more given over to the processes of growth and moisture and slow green abundance. On the leeward side, you step into a different world entirely. The air is drier. The sky is often clearer. You can see the stars on nights when the windward side is buried in cloud. The vegetation changes. The tall, moss-draped trees give way to shorter, harder, more drought-adapted plants. The grasses are different, finer, stiffer, paler gold in summer. The soil is thinner and dustier. The light is sharper, the shadows harder edged, the distance is somehow more visible. There is a clarity to the leeward side that is its own kind of beauty, spare and clean and unadorned, like a room with very little furniture and very good light. Some of the world's great deserts begin on the leeward side of mountain ranges. The Atacama Desert in South America, one of the driest places on Earth, sits in the rain shadow of the Andes. The Gobi Desert in Central Asia sits in the rain shadow of the Himalayas and the Tibetan Plateau. The Great Basin Desert of North America sits in the rain shadow of the Sierra Nevada. These vast, dry, extraordinary places exist because a mountain range intercepted the moisture that would otherwise have reached them and kept it all for the windward side. The Andes are worth thinking about for a moment as you settle deeper into wherever you are resting tonight. They are the longest mountain range on Earth, a continuous spine of peaks and ridges running nearly the entire length of South America from the tropics to the subantarctic. On their western side, facing the Pacific, the cold Humboldt Current keeps the ocean air relatively dry, and the coastline there is one of the driest on the planet. The Atacama, where some weather stations have never recorded rain at all. On their eastern side, facing the vast Amazon basin, warm, moist air from the Atlantic sweeps in and rises against the slopes, producing some of the wettest and most biodiverse rainforest on Earth. Two complete opposite worlds, separated by nothing more than a ridge of rock. The mountain range does not choose which side to favor. It simply stands, and the physics of air and moisture decides everything else. One side gets the rain, and the other gets the stars. Both sides are beautiful. Both sides are full of life that has learned exactly how to live in the conditions it was given. Please do remember to check the playlist. There are so many more of these quiet journeys waiting for you there whenever you need them. The Himalayas create weather on a scale so large that it affects the climate of the entire Asian continent. The monsoon, that great seasonal reversal of winds that brings life-giving rain to India and Southeast Asia, is shaped and directed by the presence of the Himalayan range and the Tibetan Plateau. In summer, the plateau heats up intensely, and the hot air rising from its surface draws in moist air from the Indian Ocean in a vast, continent-scale breathing motion. The mountains channel this moisture, direct it, concentrate it on certain slopes, and deflect it from others. Cherrapunji, in northeastern India, sits at the foot of a particularly steep section of the Himalayas, and it has recorded some of the highest annual rainfalls on Earth, more than 11 meters in a single year. More rain than most temperate countries receive in a decade, falling in a single monsoon season, delivered there by the shape of the mountains above. The people who live there have built their culture, their agriculture, their architecture, their daily life around this extraordinary abundance of mountain-made rain. When the monsoon ends and the winds reverse in winter, the Himalayas do something equally dramatic. They block the cold Siberian air from reaching the Indian subcontinent. Without the Himalayas, the winters of India would be dramatically colder. The cold continental air from the vast dry plateau of Central Asia would sweep southward unchecked. But the mountains stand in the way, and India's winters stay mild and pleasant, while the other side of the range endures some of the coldest temperatures on Earth. The mountain range is a climate wall, a continental scale thermostat, holding warmth on one side and cold on the other, with a patience that has lasted millions of years and shows no sign of changing. In the Alps of Europe, the same drama plays out on a smaller but no less beautiful scale. The north side of the Alps intercepts moisture from the Atlantic and produces reliable rainfall and snowfall that feed the great rivers of Central Europe. The Rhine, the Danube, the Rhone, all begin in the Alps, or are fed substantially by alpine snowmelt. The southern side, facing the Mediterranean, has a different character, drier, sunnier, with the particular quality of Mediterranean light that has drawn artists and travelers for centuries. Between these two climatic worlds, the mountain passes have been the most important corridors of human history, the routes through which people, animals, armies, goods, and ideas have moved for tens of thousands of years. The mountains shape not just the weather, but the story of human civilization in ways that are still being written. Let your body relax a little more deeply now. Feel the weight of it settling. There is nothing to carry tonight but your own breathing. Snow, when it falls on a mountain, does not simply pile up uniformly. It is shaped and sorted and moved by the wind in ways that create an endlessly varied landscape of drifts and hollows, ridges and smooth, open slopes. The wind takes the snow and rearranges it, building great cornices, overhanging lips of snow at the edges of ridges, and filling hollows with deep, dense accumulations while leaving exposed ridges nearly bare. These cornices are among the most architecturally remarkable things nature produces. They project out beyond the edge of the ridge, sometimes by several meters, held in place by their own compacted structure, casting long blue shadows down the slope below. They look impossible, a horizontal shelf of snow extending into thin air, with nothing beneath it but a long, steep drop. And yet they hold, sometimes for months, until the warming of spring or a subtle shift in the snow's internal structure causes them to release, and they fall with a sound like a held breath being let out. The snowpack that builds up on mountain slopes through winter is one of nature's most important storage systems. In the mountains of the American West, the Sierra Nevada snowpack acts as a vast reservoir, holding the winter's precipitation in frozen form and releasing it slowly through spring and early summer as it melts. This snowmelt feeds the rivers that water California's agricultural valleys, filling the reservoirs that supply water to tens of millions of people through the long, dry summer. The snowpack is measured every year. Researchers go out onto the mountain slopes and push a hollow tube into the snow and pull out a core and weigh it, measuring the water content of the season's accumulation. The number they get tells farmers how much irrigation water they can expect, tells cities how carefully to ration their supplies, tells the whole intricate civilization of the region what kind of summer it will have. The mountain holds this information in its snow and releases it slowly as needed at the pace of the melt. The process by which snow turns to ice, by which the loose, light, airy crystals of fresh snow compact over years into the dense blue ice of a glacier, is one of slow transformation that changes everything about how the frozen water behaves. Fresh snow is mostly air. It is light and fluffy and catches the light on its surface in a million tiny sparks. Over time, under the weight of new snow above, the crystals pack together, the air is squeezed out, and the structure becomes denser and more compact. Over years, this compacted snow, called firn, becomes glacier ice, dense, heavy, nearly incompressible, deep blue-green in color when seen from inside a crevasse. Glacier ice moves. This is perhaps its most remarkable property. Under its own weight and the pull of gravity, glacier ice flows downhill, slowly, far too slowly to watch directly, but measurably, over months and years. A glacier is a slow river of ice, and like a river, it carves and shapes and transports and deposits. The mountain valleys that glaciers have carved have the distinctive U-shape that engineers admire for its perfect structural efficiency. Steep sides, flat floors, exactly the shape that a body of ice moving under pressure would produce. If you find yourself drifting now, that is exactly right. Let the story be a current beneath you. You do not need to hold on to it. The wind on mountain ridges does things that wind in other places does not do. It creates features in the snow and ice and even the rock that are entirely its own. Sastrugi, parallel ridges of hard snow carved by the prevailing wind, give high snowfields the texture of a frozen sea, all the waves running in exactly the same direction, parallel and regular as if combed. Walking across Sastrugi is one of the more meditative experiences available on a mountain. Each step the same as the last, the pattern repeating indefinitely, the horizon perfectly level, the sky enormous above. Wind also carves rock over long enough time scales. The stones of high ridges that have been exposed to the wind for thousands of years are polished smooth on the windward side, etched and pitted on the sheltered side, and shaped overall into aerodynamic forms that could have come from an engineer's dream. Rounded leading edges, tapered trailing edges, exactly the form that minimizes resistance to the flow of air. The mountain teaches aerodynamics, if you look carefully enough at its stones. Mountain gaps and passes are places where the mountains are lower and the wind can flow through rather than over. These gaps act as funnels, accelerating the wind as it is compressed through the narrower space. The winds in certain passes are so reliable and so strong that they have been given names and personalities by the people who live near them. The Mistral of the Rhone Valley in France comes from the north through the gap between the Alps and the Massif Central and arrives on the Mediterranean coast, cold and strong and very dry. The Föhn, which flows down the northern slopes of the Alps after losing its moisture on the southern side, is so warm and dry that it can raise temperatures in alpine valleys by 10 or 15 degrees in a matter of hours, softening the snow, bringing the smell of spring to February, creating a strange and slightly uneasy brightness in the air. The people of these regions have known and named and described these winds for centuries. The mountain sends them reliably, and the people have learned to read them the way others read calendars. A gentle like, if you're enjoying this journey, is always appreciated. It helps this channel reach more people who might need a quiet place to rest. There is a cloud formation that appears only over mountains, and it is one of the most beautiful things the sky produces. It is called a lenticular cloud, and it forms when stable, moist air encounters the wave that a mountain creates in the atmosphere on its leeward side. When a smooth, layered flow of air is disturbed by a mountain, it does not simply tumble into chaos on the other side. Instead, it forms standing waves, regular, repeating oscillations in the airflow that can extend for hundreds of kilometers downwind of the peak. These waves are invisible, but where their crests lift moist air above the condensation level, a cloud forms. And here is what makes lenticular clouds remarkable. The cloud itself does not move. The air flows through it, rushing in on the windward side, condensing briefly into droplets, then evaporating again on the leeward side as the air descends and warms. The cloud is a fixed structure in a moving medium, the way a wave on a river is fixed, even though the water flows through it. The shape is perfectly oval, perfectly smooth, with no ragged edges or wisps. It looks like nothing so much as a lens, or a disc, or something that was placed there deliberately by something that cared about symmetry. Lenticular clouds can stack. When there are multiple layers of moist air at different altitudes, each layer can produce its own lenticular cloud at the crest of its own wave. The result is a stack of smooth, perfectly horizontal discs above the mountain peak, each one slightly smaller than the one below, tapering to a point at the top. This formation is so extraordinary and so unlike anything else in the sky that it has, for centuries, led people to report seeing things that were not there, to reach for explanations that were not meteorology, but imagination. It is hard to blame them. A stack of lenticular clouds above a mountain at sunset, the lower clouds lit amber and the upper ones still white against a darkening sky, is one of the most genuinely strange and beautiful things available to human eyes. It requires no enhancement. It is exactly as extraordinary as it looks. The mountain that is most famous for its lenticular clouds is perhaps Roraima in South America, the flat-topped tepui that rises sheer from the surrounding jungle and seems to inhabit its own microclimate of perpetual cloud and mist. But lenticular clouds appear wherever the conditions are right. Over Fuji in Japan, over Etna in Sicily, over the Matterhorn in Switzerland, over Rainier in Washington State. Each mountain produces its own version, shaped by its own particular height and slope, and the particular character of the winds that arrive there. No two lenticular clouds are alike, because no two mountains are alike, and no two wind conditions are alike. Each one is a unique collaboration between a particular piece of stone and a particular movement of air, existing for a few hours and then dissolving as the conditions shift, leaving the sky empty and ordinary as if nothing had happened there at all. You are doing beautifully, just breathing, just resting, just letting the story move through you like wind through a cloud. Above the clouds, the mountain continues. The upper slopes are a different world from the cloud forest below, harder, colder, more exposed, stripped of the softening influence of moisture and vegetation. The rock here is bare or nearly bare, dusted in places with lichen, the remarkable organisms that are technically two things at once, a fungus and an alga living in such intimate partnership that they behave as a single creature. Lichen grows on rock by producing acids that slowly dissolve the mineral surface, extracting the nutrients it needs from the stone itself. It is one of the slowest forms of growth on Earth. Some individual lichen colonies on Arctic and alpine rock are thousands of years old, having grown by less than a millimeter per year since before recorded human history began. And yet, they are covering the mountain's upper rocks with color, gray and green and bright orange and sulfurous yellow, painting the stone with slow, ancient patience. They are the mountain's oldest residents, and they were here long before anything else could survive at this altitude. At a certain height, higher in the tropics, lower near the poles, the mountain crosses the tree line. Below the tree line, trees grow. Above it, they do not. The tree line is not a sharp edge, but a gradual transition, a zone of increasingly small, increasingly wind-shaped trees that lean away from the prevailing wind, growing in shapes that describe perfectly the force and direction of the wind that has been shaping them. These trees are called Krummholz, a German word meaning crooked wood, and they are among the most characterful plants on earth. They may be centuries old growth by any reasonable standard, and yet they grow only a meter or two tall, their trunks and branches pressed close to the ground for protection, their growth concentrated on the leeward side, where the wind does not reach. A Krummholz tree at the tree line is a record of every winter it has survived, every storm that has scraped over it, every spring that has given it a few weeks to add a millimeter or two of new growth before the cold returns. They are small and immovable and utterly magnificent. Above the tree line, the wind is unimpeded. There is nothing to slow it, nothing to break it, nothing to diffuse its force. The wind here has a directness and a physicality that lower altitude wind does not have. It is not aggressive, or at least on mild days it is not, but it is present in a way that is difficult to ignore. It presses against you steadily, finding every gap in whatever you are wearing, moving your hair and your clothing, and occasionally making you take a step sideways to keep your balance. The sound of it is the sound of something that has traveled a very long way and has no intention of stopping. It comes from the west or the north, or wherever the prevailing winds of that latitude happen to blow, and it has been crossing ocean and plain and lower hills to get here, and it will continue past this mountain and on to wherever it is going, and your presence in it is a brief and inconsequential interruption. This is strangely comforting. The wind does not notice you. You are simply in its way for a moment, and then it continues. Please take a moment, if the feeling moves you, to like this video. It is a small thing for you and a meaningful one for this channel. At the very highest altitudes, where the air is thin and the cold is profound and the mountain's summit finally arrives, the weather is governed by forces that operate at a planetary scale. The jet stream, that river of air that circles the entire planet at the level of the tropopause, the boundary between the lower atmosphere and the stratosphere, sometimes descends close enough to the highest peaks to affect them directly. Everest, K2, the peaks of the Karakoram, and the Hindu Kush. These mountains are tall enough to reach into the lower edges of the jet stream on days when the stream dips. When this happens, the wind at the summit can exceed 100 kilometers per hour, or 200 or more. No living thing can remain in such wind. The snow is stripped from the rock and driven horizontally with a force that would shred an unprotected person in minutes. And yet, in the brief windows when the jet stream lifts and the wind calms, these summits are among the most serene places on earth. Cold and clear and utterly still, the curvature of the earth visible, the sky above darker than at lower altitudes, the stars during the day almost visible at the edges of vision. The weather window, the brief period of relative calm between storm cycles, is one of the most important concepts for anyone who spends time in the high mountains. Weather on high peaks changes far more rapidly than weather at lower altitudes. A clear morning can become a whiteout by noon. A week of perfect blue sky can be followed by 3 days of storm without a day of warning. The mountain makes its own weather quickly and can unmake it just as quickly. The same dynamics that produce a beautiful lenticular cloud in the morning can produce a thunderstorm by afternoon if the atmosphere's stability shifts. The mountain does not make promises. It offers conditions, and the conditions change. This is not threatening. It is simply the nature of a place where the atmosphere is active and alive and doing its constant work of moving energy and moisture around the planet. Let the evening settle around you now. Let your thoughts drift the way clouds drift, without direction, without urgency, carried by something larger than themselves. The temperature lapse rate, the rate at which temperature decreases with altitude, is one of the most fundamental facts of mountain weather, and it shapes everything about how mountains create their climates. In dry air, the temperature drops about 10 degrees Celsius for every 1,000 meters of altitude gained. In moist air that is actively producing cloud and rain, the rate is about 6 degrees per 1,000 meters, because the condensation of water vapor releases heat into the air and slows the cooling. This difference between the dry adiabatic rate and the moist adiabatic rate is the key to understanding why the windward side of a mountain is warmer than the leeward side, even though both sides are at the same altitude. The air that rose on the windward side, cooling at the moist rate, giving up its moisture as cloud and rain, now descends on the leeward side, warming at the dry rate, faster, because it has lost its moisture. It arrives in the leeward valley warmer and drier than when it started its journey on the other side. This is the Foehn effect, and it explains why the winds that come over mountain ranges from one side always feel warmer and drier on the other side, as if the mountain has somehow added heat to the air rather than simply letting it pass through. In the Rocky Mountains of North America, this descending warm, dry wind is called the Chinook. It arrives on the eastern plains of Alberta and Montana with such warmth that it can melt a meter of snow in a single day, so quickly that the snow seems to vanish rather than melt, sublimating directly from solid to vapor without going through the liquid phase. Ranchers on the eastern slopes have stories of Chinook winds raising the temperature by 30 degrees in an hour, of cattle standing in a snowstorm one moment and sunshine the next as the warm front swept through. The word Chinook comes from a Native American people whose homeland was in the Pacific Northwest. The wind that came from that direction over the mountains, carrying warmth when warmth was most welcome. It is a wind with a name and a history and a character that people have known and depended on for generations. The mountain makes it. The people named it. And every winter it arrives as reliably as a friend. The clouds that build over mountains in summer are not all the same. There are the gentle, layered stratus clouds that wrap the mountain in gray mist on mild days, so low that you walk into them without noticing where the air ended and the cloud began. There are the rounded cumulus clouds that form in the warming afternoon air and drift slowly across the slopes, their shadows moving across the green hillsides below at the pace of a slow walk. And there are the cumulonimbus, the great storm clouds, the vertical monsters that can rise 15 or 20 kilometers from base to top, containing updrafts of 100 kilometers per hour and more, producing lightning and hail and rain of extraordinary intensity. On a hot summer afternoon over a mountain range, you can watch a cumulonimbus build in real time, the cloud towers growing visibly upward, minute by minute, the top spreading out into the distinctive anvil shape as it hits the stable air of the upper atmosphere and can rise no further, flattening and spreading downwind like smoke from an enormous chimney. The anvil is the sign that the storm has reached its full development. It is both beautiful and humbling, and it is entirely the mountain's creation. The lightning that comes with these storms is one of nature's most startling phenomena, and it is deeply connected to the mountain's role in generating weather. Lightning is the result of electrical charges separating within a cloud, positive charges accumulating near the cloud's top, negative charges near its base. The separation driven by the violent updrafts and downdrafts within the thunderstorm. When the charge difference becomes large enough, it discharges a bolt of lightning, heating the air through which it passes to temperatures 5 times hotter than the surface of the sun instantly for a fraction of a second. The thunder that follows is the sound of that superheated air expanding explosively. On mountains, lightning strikes exposed ridges and peaks with much greater frequency than it strikes flat ground, because the peaks are closer to the charge-laden base of the cloud, and because the topography channels the electrical discharge. Tall, isolated trees on mountain ridges often show the evidence of repeated strikes: split trunks, bark stripped in long spirals, branches missing. And yet, the trees keep growing. They are not killed, usually just reshaped. The mountain's lightning leaves its mark, and the mark becomes part of the tree's character. The thunder in a mountain valley is different from thunder in open country. The valley walls reflect and channel the sound, so that a single roll of thunder becomes a long, reverberating conversation between the slopes. The sound bouncing from one wall to the other, arriving at your ears from multiple directions in sequence, overlapping and fading and overlapping again. It can last for many seconds after the original lightning strike, growing softer with each reflection until it fades into something more like a distant rumble than a sharp crack. If you have ever been in a mountain valley during a thunderstorm and found yourself a safe place to watch from, under a good solid overhang, away from anything tall and isolated, the experience of listening to thunder echo through the valley is one of the most sonically rich available in nature. It fills the air completely and then releases it, leaving a silence that seems deeper than the silence before the storm, as if the thunder has swept the valley clean. Take a slow breath. Let your shoulders settle. You are safe and warm, and the mountain's thunder is very far away tonight. Rain in the mountains has a smell that is specific and unmistakable. It is called petrichor, from the Greek petra, meaning stone, and ichor, the fluid that in Greek mythology flows in the veins of the gods. Petrichor is produced when rain falls on dry rock or soil and releases compounds that have been trapped there. Geosmin, produced by soil bacteria, which smells of earth and growth and dampness. Plant oils that have been absorbed into the rock surface during dry weather and released in tiny aromatic puffs when the water arrives. Ozone, produced by lightning, which smells electric and clean and slightly sharp. All of these compounds arrive together in the first moments of rain, and together they produce the smell of rain beginning, one of the most universally recognized and almost universally loved smells that exists. On a mountain slope, where the rock is bare and ancient, and the soil is thin but rich with bacterial life, this smell is particularly intense. The first drops of a mountain shower release it all at once, and for a moment the air is so full of it that it is almost visible, almost something you could reach out and touch. Mountain fog is different from valley fog in its behavior and in its feeling. Valley fog tends to be still. It settles and lies flat and burns off when the sun warms it. Mountain fog moves. It drifts along the slope, thinning and thickening, parting and closing. You can be in clear air one moment and deep in cloud the next, not because you have moved, but because the cloud has. Walking in mountain fog is a particular experience. The world contracts to a circle of perhaps 10 or 20 meters around you, and everything outside that circle is white. Sounds seem to come from different directions than they should. The slope, is there feels uncertain. It is not frightening exactly, but it is humbling. A reminder that the mountain knows where it is, and you do not. Not quite. The fog takes the mountain scale away and gives you back something more intimate. Just the rock beneath your feet, the wet grass to either side, the white all around, and the sound of your own breathing, which is very close and very clear. Do check the playlist when you get a chance. There are stories there for every kind of night, and each one is waiting for you like a light in a window. The clouds that cling to high mountain peaks in the tropics are a permanent feature of the landscape in many places, not seasonal, not occasional, but constant. The great volcanic peaks of East Africa, Kilimanjaro, Mount Kenya, the Ruwenzori Mountains, wear their clouds the way they wear their glaciers, as a permanent part of their appearance, an aspect of their identity. The clouds form every day as the moist air from the surrounding savanna and forest rises against the flanks of the mountains and condenses in the cooler altitudes. They hang at a certain level, the cloud forest zone, and below them the world is open and sunny, and above them the peaks rise into clear air. To walk up through this cloud layer is to pass through a threshold. You step from the warm, bright, buzzing world of the lower slopes into a cool, muffled, dripping world of fog and moss and the sound of water falling from leaves. The transition is immediate and complete. One step in the sun, the next in the cloud, and you have crossed from one world into another without going anywhere unusual at all. The cloud forests of tropical mountains are among the most biologically diverse habitats on Earth. The constant moisture, not just from rain, but from the cloud itself, which deposits water directly onto leaves and bark as the mist flows through, supports an extraordinary density and variety of life. The trees are festooned with epiphytes, plants that live on other plants without being parasitic, drawing their moisture from the air and their nutrients from the dust and debris that accumulates in cracks and hollows. Bromeliads and orchids and ferns crowd every horizontal surface. Mosses several centimeters thick cover every trunk and branch. The ground is soft with decomposing plant material, and it squelches gently underfoot. Everything is dripping. Everything is alive. The mountain makes this possible simply by being tall enough to intercept the cloud and hold it at the right altitude for the right number of hours each day. Remove the mountain, and all of this life, this irreplaceable, extraordinary accumulation of living things, would not exist. As the night deepens wherever you are, let your body grow heavier and softer, like rain-soaked moss, settled and still. The water that drips from the leaves of cloud forest trees is doing something more than simply falling. It is carrying. Every droplet contains dissolved minerals leached from the leaf surface, organic compounds produced by the epiphytes, particles of biological material that will fertilize the soil when the droplet reaches the ground. The fog drip from a single large tree in a cloud forest can add hundreds of liters of water to the soil on a foggy day. Water that did not fall as rain, that came entirely from the cloud flowing through the tree's crown. This is an important contribution to the water budget of the whole mountain ecosystem. In some cloud forests, the fog drip from the trees contributes more water to the streams below than the rain itself. The trees are harvesting the cloud, drawing water from the air with their leaves, the way the roots draw water from the soil, and what they collect drips down and feeds the streams that run from the mountain. The mountain's cloud creates the forest harvests the cloud feeds the streams water the valleys below. The whole system depends on the mountain being tall enough and positioned correctly to intercept the cloud. It is a chain of dependence so elegant that it seems designed, even though it arrived here through millions of years of accident and adaptation. Some mountains in coastal regions produce fog so reliably that they function as the primary source of fresh water for the ecosystems that surround them. The coastal mountains of the Atacama Desert in Chile and Peru receive almost no rain, less than 1 millimeter per year in some places, and yet they support a remarkable community of plants and animals because they intercept the fog that rolls in from the cold Pacific Ocean. These plants, the lomas they are called, the meadows, bloom for a few months each year when the fog is most frequent, producing flowers of extraordinary beauty in one of the driest landscapes on Earth. They exist entirely because of what the mountain does to the fog. The mountain takes something diffuse and abundant, the fog that covers the whole coastline, and concentrates it on its slopes, giving plants just enough moisture to live and flower and set seed before the fog retreats and the dry season returns. Life on these fog mountains is delicate and extraordinary, and it is entirely the mountain's gift. There is a mountain in Washington state called Rainier, and it earns its name. The moist air from the Pacific Ocean arrives at its flanks with extraordinary generosity, giving up its moisture so readily that the mountain's higher slopes receive some of the greatest snowfall totals ever recorded anywhere on Earth. In the winter of 1971 to 1972, the Paradise Rangers station on Rainier's southern flank received over 29 meters of snow, more snow in a single winter than some places receive in a lifetime. This is mountain weather on a grand scale. The ocean's moisture, the mountain's lift, the cold of altitude, all combining to produce quantities of snow that seem almost impossible. And yet, Rainier wears this snow calmly, as it wears everything. The glaciers that flow from its summit, the wildflower meadows of its lower slopes, the cloud forest of its middle elevations, the bare volcanic rock of its upper reaches. The mountain holds all its weather with the same stillness. It does not distinguish between the extraordinary and the ordinary. It simply receives what the atmosphere sends and holds it until the season turns and the melt begins. The glaciers that flow from Rainier and from other heavily glaciated mountains are rivers of ice in the most literal sense, and they create their own microweather as they do so. The cold air that sits over a glacier flows off its surface and down the valley below, just as katabatic air flows from a mountain summit at night. This glacier wind is reliable and cold and carries the particular smell of ice, clean and slightly metallic, like the smell of very cold water. Plants at the edges of glaciers grow in patterns that reflect this cold wind. The vegetation closest to the ice is low and cold adapted, giving way gradually to more temperate plants at increasing distances. The glacier creates a climate zone around itself, a bubble of cold that extends for some distance into the warmer world around it. As glaciers retreat, as many of them are doing now, pulling back up their valleys, the climate zones they created shift and change. Flowers that grew in the cold fringe of the glacier find themselves in warmer air. New plants move in. The mountain's local climate changes not from anything the mountain does differently, but from what the ice is no longer doing. You might feel your breathing slowing now, growing more regular, more effortless. That is the mountain's influence, even from here. The way ice melts on a mountain is not uniform. Different aspects of the mountain, different slopes and faces, receive different amounts of sunlight at different times of day and at different seasons. And so they melt at different rates and lose their snow cover at different times. A south-facing slope in the northern hemisphere receives more direct sunlight than a north-facing slope, and so its snow melts weeks earlier in spring. The plants that grow on south-facing mountain slopes are therefore different from those on north-facing slopes. More drought-adapted, more sun-tolerant, blooming earlier in the year. On a mountain that has both aspects in close proximity, you can sometimes see this difference very clearly. A ridge with its south face already green and flowering, and its north face still covered in snow. Two seasons existing simultaneously on opposite sides of the same ridge of rock. The mountain holds spring and winter next to each other, separated by nothing more than the angle at which the stone faces the sun. Snow crystals, the individual crystals that make up a snowflake, form in clouds in one of several basic shapes, and the shape they take is determined precisely by the temperature and humidity of the air in which they form. At temperatures just below freezing, the crystals tend to be thin and plate-like. At lower temperatures, they become needle-shaped. At still lower temperatures, they take on the complex branching dendritic forms, the six-armed stars, that most people picture when they think of snowflakes. And at the very coldest temperatures, near minus 40 degrees, they become simple hexagonal columns again. Moving through a cloud, a falling crystal passes through different temperature zones and picks up characteristics of each one, adding arms at one level, plates at another, becoming the unique structure that it is through the particular journey it has taken through the particular cloud on the particular day it was made. No two journeys are exactly alike, and so no two snowflakes are exactly alike. The mathematics of this uniqueness is staggering. The number of possible arrangements of water molecules in a snowflake exceeds the number of atoms in the observable universe by an incomprehensible margin. And yet, each one falls quietly on the mountain and becomes part of the snowpack, indistinguishable from its neighbors, its extraordinary uniqueness dissolved into the collective white. The snowpack on a mountain is not a passive thing. It is constantly changing, shifting, settling, transforming. The crystals at the surface are exposed to sun and wind and temperature fluctuations that change them continuously. They grow larger, they bond together, they break apart, they sublimate directly from solid to vapor on cold, dry days, adding moisture to the air without ever melting. Deeper in the snowpack, away from the surface fluctuations, the crystals are changing more slowly but just as surely, recrystallizing into larger, more rounded grains as the pack consolidates under its own weight. Within the pack, thin layers of ice form where rain has penetrated and refrozen, or where the surface melted on a warm day and then froze again at night. These ice layers, sandwiched in the snowpack, are records of past weather. A cold spell here, a warm spell there, a rainy period, a long dry freeze. You could read the winter's weather history in a cross-section of the pack, the way you read a tree's history in its rings. The mountain writes its weather in its snow, and the snow holds the record faithfully until spring. If you're finding peace here tonight, a like on this video is a lovely way to share that peace with others who might need it too. The processes that govern snow stability, that determine when a slope is safe and when an avalanche is waiting to happen, are entirely weather-driven. Avalanches occur when the weight of snow above a weak layer in the snowpack exceeds the strength of that layer to hold it. The weak layers are created by specific weather conditions, periods of cold, clear weather that allow surface crystals to grow large and faceted and weak, rapid loading of new snow on an existing pack, rain that lubricates the interface between layers, rapid warming that reduces the friction between snow and the slope beneath. A slope that has been stable all winter can become unstable in an hour, given the right weather trigger. The mountain's weather writes the avalanche hazard as surely as it writes everything else about the mountain's snow. And when an avalanche does release, it creates its own brief and violent weather. A cloud of snow dust that rises hundreds of meters above the slide path, a pressure wave that can break trees at the margins, a wind that moves ahead of the slide clearing its path, a roar that is entirely unlike thunder, deeper, more physical, felt in the chest as much as heard in the ears. And then silence. The mountain returns to stillness. The debris field settles, the snow settles, and the slope begins again, slowly, the long process of building a new snow pack. High mountain lakes deserve their own quiet celebration because they are among the most serene places on Earth, and they exist entirely because of the mountain's weather. They form in basins carved by glaciers, those deep, rounded hollows called cirques or tarns that fill with snowmelt and rainwater and are fed through the year by the slow seepage of groundwater through the surrounding rock. The water in these lakes is almost impossibly clear. It has been filtered through rock and gravel and the slow percolation of snowmelt, and it carries almost nothing. No silt, no organic material, very little dissolved mineral. You can see the bottom at depths where you would not be able to see it in a lowland lake. The pebbles on the bed are vivid and detailed, as if seen through a magnifying glass. The colors of the water shift with the depth, pale turquoise in the shallows, deepening to a rich teal in the middle, darkening to a deep blue-green at the greatest depths. In some mountain lakes, where glacial flour, rock ground to powder by the movement of ice, remains suspended in the water, the color is an almost impossible turquoise that looks more like paint than water. On windless days, these lakes become perfect mirrors. The peaks above are reflected with a precision that seems to duplicate the world, creating a symmetry so complete that for a moment you cannot tell which is the mountain and which is its reflection. A bird crossing the reflected sky seems to be crossing the real sky. A cloud forming over a reflected peak seems to form in the lake itself. The boundary between the real and the reflected dissolves, and you stand at the edge of something that is two worlds perfectly superimposed, the only evidence of the join a faint line where the water meets the scree and the reflection begins. On days when a small wind riffles the surface, the reflection breaks into 1,000 moving fragments of light, each one a tiny version of the mountain, all of them shifting and reforming and shifting again, the mountain multiplying itself in the small waves endlessly and without effort. Let your mind rest now the way a mountain lake rests in stillness, just holding the sky, not going anywhere. The thermal stratification of a mountain lake, the way the water sorts itself into layers of different temperatures through the summer, creates one of nature's more subtle and beautiful dynamics. In summer, the surface water warms in the sun and becomes less dense, floating on top of the cold, dense water below. Between the warm surface layer and the cold, deep layer lies the thermocline, a zone of rapid temperature change where the warm water meets the cold. The thermocline acts as a barrier, preventing mixing between the two layers. The surface layer circulates and warms. The deep layer remains cold and dark and still. In autumn, as the air cools and the surface water temperature drops, this stratification breaks down. The surface water, becoming as cold and dense as the water below, sinks and mixes with it in a process called the autumn turnover. The lake stirs itself, bringing cold, nutrient-rich water from the depths to the surface. This mixing is one of the most important events in the lake's annual life cycle. It redistributes oxygen, redistributes nutrients, resets the conditions for the following year's biological activity. All of it driven by the mountain's weather, the warm summers and cold autumns that create and then destroy the stratification. The rivers that flow from mountains carry the story of the mountain's weather downstream. After a heavy rain on the upper slopes, the river rises quickly and its color changes. Clear mountain water becoming coffee brown with suspended sediment, carrying fine particles of soil and organic matter and dissolved minerals from the hillsides. After the rain stops, the river falls back to its clear state, but more slowly than it rose. The snowmelt and groundwater that sustain it continue to supply it steadily for days or weeks after the rainfall. A river hydrograph, a chart of a river's flow over time, looks different for mountain rivers than for lowland rivers. Mountain rivers rise quickly in response to storms, but their base flow, the underlying steady contribution from groundwater and snowmelt, is usually higher and more reliable. The mountain sustains the river even when the rain has stopped, releasing what it has stored in its slow, patient way. The sediment that mountain rivers carry is one of the mountain's most important gifts to the world downstream. Himalayan rivers carry enormous loads of sediment down from the mountains and deposit it on the plains of India, Pakistan, and Bangladesh, building and rebuilding the alluvial plains that are home to some of the most densely populated and agriculturally productive regions on Earth. The Nile's annual flood, which for millennia deposited a layer of rich sediment on the floodplain of Egypt, was fed by rain on the Ethiopian highlands, a gift from the mountains of East Africa to the desert civilization downstream. The mountains give their substance away, grain by grain, year by year, building the plains that feed the world, while they themselves slowly erode. They are generous to an extraordinary degree, and they do it all through weather, through the rain that falls on them and the rivers that carry them to the sea. A warm thank you to everyone who has been here with us tonight. If you haven't yet explored the playlist, it's always there. A whole library of quiet. The waterfalls that pour from mountain cliffs are another direct expression of the mountain's relationship with weather. Many waterfalls are seasonal. They exist only because of snowmelt in late spring and early summer, running full and spectacular for a few months, and then thinning to a trickle, or disappearing entirely by late summer. Others are fed by permanent springs or by the slow drainage of large snowfields and glaciers, and they run year-round, but with a seasonal rhythm of their own, high and powerful in snowmelt season, lower and quieter in autumn. The sound of a mountain waterfall changes with its volume. A full waterfall in snowmelt season produces a deep, continuous roar that you can feel as much as hear. The same waterfall in late summer, reduced to a thin curtain of water, produces a lighter, higher sound, more like the sound of rain. Both are beautiful, and both are the mountain's weather made audible. The sound of the sky's gift to the mountain being returned to the valley below. In the high Arctic and Antarctic, where the mountains are often ice-covered from base to summit, the interaction between mountain and weather takes on a stark and elemental quality that is very different from the lush complexity of tropical cloud forests, but no less extraordinary. The ice sheets and glaciers of these polar mountains generate their own weather in the most direct way. The cold of the ice cools the air above it, creating persistent katabatic winds of remarkable force. The katabatic winds of Antarctica, cold air draining from the high polar plateau down to the coast, are among the strongest surface winds on Earth. They flow down the glacial valleys with a relentless, bone-dry cold, gusting at times to 200 kilometers per hour, sculpting the snow on the valley floors into the ridged patterns of sastrugi and driving ice crystals horizontally with the force of sandblasting. And yet, in the calm between the gusts, these same glacial valleys have a silence of almost unimaginable depth, not just the absence of sound, but the presence of something positive, a profound, layered, encompassing quiet that seems to have its own texture and weight. The glaciers of Greenland and Antarctica are not simply frozen water. They are archives. The ice that forms in them comes from snow that fell thousands of years ago, layer by layer, compressing under the weight of subsequent snowfall into dense ice that preserves within it tiny bubbles of the air that was present when the snow fell. These air bubbles are samples of ancient atmosphere. They contain the same mixture of gases that existed in the atmosphere when the snow fell, whether that was 1,000 years ago or 800,000 years ago. Scientists drill cores deep into these ice sheets and extract cylinders of ice that go back through the millennia, reading the ancient atmosphere directly. The carbon dioxide and methane and oxygen that were present in the air when mammoths walked the tundra, when human civilization was still in its earliest stirrings, when the last ice age was ending and the forests were advancing northward, following the retreating glaciers. The mountain of ice is a library, and the mountain's weather, the snow that fell on it year after year, century after century, wrote every page. Rest here for a moment with the thought of all that time, all those centuries of snow, each one a quiet gift to the record. You are part of time, too, and you are doing beautifully in it. The Tibetan Plateau, sometimes called the roof of the world, is the most extreme example of how a mountain landmass can shape the weather of an entire hemisphere. At an average elevation of over 4,000 meters, the plateau covers an area the size of Western Europe and sits so high in the atmosphere that it heats up dramatically in summer, creating a vast thermal engine that drives the Asian monsoon. The plateau absorbs solar radiation and warms the air above it, creating an enormous low-pressure system that pulls in moist air from the Indian Ocean hundreds and thousands of kilometers away. Without the plateau, the monsoon as we know it would not exist, and the agriculture that feeds billions of people in South and Southeast Asia would be entirely different. The plateau also acts as a barrier to the westerly jet stream, splitting it into two branches, one flowing north of the plateau and one flowing south, and in doing so, shaping the climate patterns of the entire northern hemisphere. The mountains of Tibet are not just making local weather, they are participating in the global circulation of the atmosphere. The effect of the plateau on the jet stream creates what meteorologists call Rossby waves, large, meandering undulations in the flow of the upper atmosphere that extend halfway around the planet. These waves influence the weather of Europe and North America, determining where the blocking high-pressure systems form that create heat waves and cold spells and prolonged droughts. The mountains of Central Asia, by deflecting and splitting the jet stream, are participating in the weather of places 10,000 kilometers away. A cold winter in Europe can be traced in part to the standing waves created by the Himalayas and the Tibetan Plateau months earlier and thousands of kilometers distant. The mountain does not know this. The mountain simply stands, and the atmosphere responds, and the response travels around the world, and the world's weather is different because the mountain is there. Everything is connected at the largest scale, and the mountain is one of the connections. Please, if you're enjoying this journey, share it with someone who might need a quiet night. And the playlist is always there, a whole world of stillness just for you. The way mountains affect the path of rivers begins before the rivers exist. When rain falls on a mountain, it follows the path of least resistance downward, and the paths it carves over thousands of years become streams, and the streams carve valleys, and the valleys shape the whole topography of the mountain's lower slopes. The mountain's weather, where the rain falls most heavily, which slopes get the most precipitation, which aspects are windward and which leeward, determines where the rivers form. The watersheds of mountain ranges divide the continent into great drainage basins, each one defined by the mountain ridges that separate where the rain falls on one side from where it falls on the other. A raindrop that falls on one side of the continental divide in North America will eventually reach the Pacific Ocean. A raindrop that falls on the other side will eventually reach the Atlantic or the Gulf of Mexico. The mountain ridge makes this decision for the raindrop and has been making it for millions of years, determining the paths of rivers that are among the most important geographical features of the continent. The Continental Divide runs along the crests of the Rocky Mountains for nearly 3,000 kilometers, from Canada to New Mexico, and along its length it creates one of the most dramatic weather contrasts in North America. Pacific air masses carry moisture up against the western slopes. Arctic air masses sweep down from Canada on the eastern side. And in between, the divide separates two atmospheric worlds. Storms that reach the eastern front of the Rockies from the Gulf of Mexico produce extraordinary snow on the eastern slopes. The famous upslope snowstorms of Colorado, where moist air from the south is pushed up against the mountains and deposits snow in quantities that rival anything on the windward Pacific side. The mountains catch weather from two directions simultaneously, two atmospheric moisture sources converging on the same range of peaks, and the result is a snowpack that is one of the most important freshwater reserves in North America, feeding rivers that water the farms and cities of a dozen states. There is something about the sound of wind in different mountain environments that deserves a moment of attention because it is one of the most varied and beautiful soundscapes in the natural world. Wind in a pine forest on a mountain slope has a particular sustained note, a low, continuous rushing sound that varies slightly as the gusts rise and fall, but maintains a consistent tone, like an organ note played very softly and without vibration. Each tree contributes its own slight variation, the density of its needles, the diameter of its trunk, the flexibility of its branches, and the combined sound is something richer and more textured than any single tree could produce. A choir of soft voices all speaking at once in a language that is entirely sound and no meaning. You can rest inside that sound. It asks nothing of you. It simply continues. As the wind continues, as the mountain continues, filling the air with its gentle complexity and asking only that you breathe. Wind through broadleaf trees on a mountain is a more dramatic sound. The leaves producing a rustling, flickering sound that is less continuous and more varied, each leaf catching the wind independently and creating its own small flutter. When the wind is strong and the trees are in full leaf, the sound builds into something that is almost watery, a rushing, shimmering sound that moves through the canopy in waves as gusts travel through the forest. When the wind drops, the sound fades in waves too, receding from one tree to the next until it is gone, and the brief silence before the next gust is almost visible in its completeness. In autumn, when the leaves are dry, the sound of wind in a mountain forest becomes more papery and more fragile, the leaves detaching and joining the wind, becoming part of the sound spinning and settling and joining the deep carpet of the forest floor, which absorbs the sound of the next gust with a soft, muffled warmth. Let your thoughts be like leaves tonight, just resting where they fall. No need to arrange them. No need to do anything with them at all. Wind through a mountain pass makes a sound that you feel more than hear. A low, resonant tone created by the compression of air through the gap, like blowing across the top of a bottle, but at an enormous scale and a very low pitch. The pass acts as a resonant chamber, and on certain days, in certain wind conditions, it produces tones that seem to come from somewhere below hearing, felt in the chest and the bones, rather than processed by the ears. Ancient peoples attributed these sounds to the spirits of the mountains, to voices speaking in a language just beyond comprehension, and this is not an entirely unreasonable response to the experience. The mountain is speaking through the wind, after all, making itself heard through the shape of its landscape and the movement of air through that shape. The sound is the mountain's voice in the most literal physical sense. The wind measurements taken at the summits of high mountains are among the most extreme wind speeds ever recorded anywhere on Earth's surface. On the summit of Mount Washington in New Hampshire, which at only 1,917 meters is not particularly high as mountains go, but which occupies a position at the intersection of several major weather systems. A wind speed of 372 kilometers per hour was recorded in 1934, and this record stood as the highest surface wind speed ever measured for the next 76 years. The mountain is not particularly tall, but it is extraordinarily well positioned to catch the collision of cold Canadian air masses with warm Atlantic air masses and the jet stream when it dips low enough to touch the summit. Mount Washington has been called the world's worst weather, which is perhaps unkind, but not inaccurate from the perspective of human comfort. From the perspective of meteorology, it is one of the most fascinating natural weather stations on Earth, and the observatory that has operated on its summit since 1932 has accumulated a record of mountain weather observations that is essentially unparalleled. A quick, friendly reminder: if you're new here, the playlist is full of nights exactly like this one, waiting for you whenever you need them. The jet stream, which we have visited briefly before, deserves more attention because it is the single most important weather-making force at the latitude of most of the world's great mountain ranges, and its interaction with those ranges is continuous and complex. The jet stream is a narrow ribbon of very fast-moving air in the upper troposphere, typically at altitudes of 9 to 12 kilometers, that flows generally from west to east around the globe. Its speed varies from perhaps 90 kilometers per hour at its edges to over 300 kilometers per hour at its core. It meanders north and south in large waves, the Rossby waves we mentioned earlier, and its position in any given week determines much of the weather that the regions below it will experience. Where the jet stream dips south, cold air from polar regions flows down into lower latitudes. Where it curves north, warm air from the tropics extends its reach toward the poles. The mountains of the world perturb and channel and deflect the jet stream, creating the standing waves and persistent patterns that determine the large-scale weather of entire regions. The interaction between the jet stream and the Tibetan Plateau is particularly important for understanding world weather. The plateau splits the jet stream into two branches in winter, a northern branch that flows along the northern edge of the plateau, and a southern branch that flows along its southern edge over the Himalayas. In summer, as the plateau heats up and the Asian monsoon develops, the jet stream shifts northward entirely, and the southern branch disappears. This seasonal shift of the jet stream, driven by the heating and cooling of the plateau, is one of the primary drivers of the monsoon's timing and intensity. When the jet stream shifts north in spring, it signals the beginning of the monsoon season for hundreds of millions of people across South and Southeast Asia. The mountains do not just make local weather, they participate in the planet's atmospheric circulation at the deepest level. The morning mist that fills mountain valleys is one of the most reliable and most beautiful of all mountain weather phenomena. On clear nights following warm days, the valley floor radiates its heat rapidly into the clear sky, and the air near the surface cools. When the air cools below its dew point, the temperature at which it can no longer hold all its moisture, fog forms. This fog is dense near the ground and thins toward the sides of the valley, often filling the valley bottom with a smooth white surface, while the slopes above and the peaks above those are in clear air. By the time the sun is fully up, the fog layer is illuminated from above, glowing white and soft and perfectly flat, the mountain peaks rising from it like islands in a calm, white sea. This is one of the images that people who have seen it once return to again and again in memory. The valley fog seen from above, the peaks rising from it, the extraordinary stillness of a world divided into fog and clarity, cloud and stone. Within an hour or two of sunrise, the fog begins to dissipate, not from the edges, but from the interior. As the sun warms the fog layer and the rising temperature allows the air to reabsorb the moisture it has condensed, the fog thins, and through it, the shapes of the valley begin to appear: trees, a farmhouse roof, the shining line of a river. Then it is gone, and the valley is clear, and the day has fully arrived. This process happens so regularly in mountain valleys, particularly in autumn, that farmers and villagers who live in them have detailed knowledge of when the fog will form and when it will clear, and they plan their days accordingly. The mountain's weather is legible if you pay attention. It has patterns, it has rhythms. It gives itself away to those who live with it long enough to read its signs. Let your body be very heavy now, very soft. Let the bed hold you completely. Let go of any last tension you might be carrying. The particular quality of light in mountains at different times of day is something photographers and painters have pursued for centuries and never quite captured, because it is as much a physical sensation as a visual one. At dawn, the light arrives first on the highest peaks, the alpenglow, a flush of deep pink and rose that touches only the summits and the highest ridges, while the valleys are still in blue shadow. This light is caused by the low angle of the sun sending its light through the greatest possible thickness of atmosphere, filtering out the blue and leaving only the warm reds and pinks. It lasts only minutes, and then the sun clears the horizon and the light changes, becoming less dramatic but more complete. The alpenglow in reverse, called the afterglow, happens at sunset, the last light touching the highest points as the sun is already set for the valley below, giving the peaks a last brief blazing of color before the blue shadow climbs up from below and extinguishes it. In the middle hours of the day, the light in mountains has a clarity that is a direct result of the mountain's weather. The air at altitude has been cleaned by cloud and rain, and what remains is some of the clearest, cleanest air available on Earth. At high altitude, the shorter wavelengths of light, the blues and violets, are scattered by the thin atmosphere more completely than at sea level, making the sky a deeper, more saturated blue than you see at lower altitudes. The shadows are sharper and bluer. The highlights on snow and rock are more brilliant. Everything is more itself, as if seen at a slightly higher resolution than usual. This quality of light is the mountain's own production. It is the result of the mountain's weather having cleaned and thinned the air, and of the reduced atmosphere above, allowing more of the spectrum to reach the eye unfiltered. At sunset and sunrise, mountain weather creates color in the sky that would be impossible without the mountain's own cloud production. Lenticular clouds catch the setting sun and hold its color long after the sun has passed below the horizon, glowing orange and gold and deep rose against a sky that is already darkening above them. High cirrus clouds, ice crystal clouds formed from the moisture that has risen above the lower cloud layers, diffuse the sunset light into broad, soft washes of color that fill the entire western sky. On particularly clear evenings, when the sunset has produced exceptional color, the opposite sky, the eastern horizon, shows the belt of Venus, a pink and mauve band just above the horizon that is the reflection of sunset color on the atmospheric haze, separated from the gray of the Earth's shadow by a clear band of the horizon itself. All of this is weather, and all of it is beautiful, and the mountain participates in every aspect of it, having produced the clouds that catch the light, having cleaned the air that transmits it, having shaped the valley that frames it. An encouraging like or comment, whenever the feeling comes, is always a quiet gift to this channel. Dew on mountain plants is a form of precipitation that is easy to overlook but enormously important. On clear nights, plant surfaces cool rapidly through radiative heat loss, and the moisture in the air near the plant's surface condenses onto the leaf as dew. This dew can be a significant source of water for plants in regions where summer rain is scarce, providing moisture during the night that sustains the plant through the following day. Mountain grasses in particular are efficient dew collectors. Their narrow, upright leaves present a large surface area relative to their volume, and they channel the dewdrops efficiently down to the base of the plant where the roots can access it. On a clear mountain morning, the meadows shine with dew, every grass blade holding its drops, every flower catching the light on its beaded surface, the whole meadow glittering before the sun warms it and the dew evaporates into the rising air, adding to the moisture of the mountain's atmosphere and perhaps contributing, eventually, to the cloud that forms by afternoon. We have come a long way together on this mountain tonight. From the base, where the air first changes its character and the wind begins its long climb, to the summit, where the jet stream occasionally reaches down and touches the stone with the force of the whole planet's atmosphere behind it. We have been in the cloud forest and above it, in the snow and in the rain shadow, in the valley fog and in the clear air above the cloud layer, where the sun shines on a white sea and the peaks stand like islands. We have met the animals that the mountain's weather has shaped, the bar-headed goose flying over the Himalayas in the dark, the mountain hare in its hollow coat, the edelweiss in its woolly insulation, the salmon reading the mountain's chemistry home through 1,000 miles of ocean. We have listened to the thunder echo in the valley, and the wind sing through the pass, and the snow fall in the perfect silence of a still winter night. The mountain does all of this, makes all of this weather, shapes all of this life, writes all of this climate. Through stillness, it does not move, it does not initiate, it does not choose. It simply stands in the path of the wind and the rain and the sun, and it offers its shape to the atmosphere, and the atmosphere responds. The mountain is a collaborator, a participant, a presence that changes everything around it simply by being there. There is something in this that speaks to something deep and quiet in us. The idea that you do not have to do anything dramatic to change the world around you. You only have to be present consistently in the right place, and the world will organize itself around you. The mountain teaches this without words. The mountain has always been teaching this, and the wind has always been learning from it, and the cloud has always been the evidence. Let the image of the mountain stay with you as you fall asleep. Let it be very solid and very still in your mind. The dark stone, the white snow, the cloud that wraps the summit like a shawl. The mountain does not sleep exactly, but it rests. It is resting now under the stars, under the turning sky, under the slow passage of weather that it has been shaping for millions of years and will continue to shape for millions more. Its rivers are running in the dark, carrying the day's melt toward the sea. Its trees are breathing, releasing the moisture they gathered today back into the air. Its smallest creatures are tucked into crevices and burrows, their bodies slowed by the cold, but still warm inside, waiting for morning. Its snowpack is settling, grain by grain, into the quiet accumulation of winter. The mountain is very patient. It has learned patience from the only teacher capable of teaching it: time. Vast, unhurried, immeasurable time. And tonight, for a few hours, you're learning patience from the mountain. The same patience, the same stillness, the same quality of simply being present and letting the world do what it does around you. Your breath is slower now than when we began. The world outside is quieter. The day is very far away, and the night is very close, and the mountain is somewhere in the dark, breathing its slow breath of cloud and wind. There is nothing to hold on to tonight. No thought that needs to be finished, no problem that needs to be solved, no question that needs its answer before morning. The mountain holds everything: the cloud and the snow and the river and the wind, and it is holding this moment too. You are inside the mountain's weather in the most gentle sense. You are wrapped in the same air that the mountain wraps in cloud, the same stillness that the mountain makes in its valleys on windless nights, the same deep quiet that falls over the alpine meadow when the last bird has gone to roost and the flowers have closed and the stars have appeared one by one above the summit. Close your eyes now, if they aren't already closed. Feel the warmth of where you are, the warmth of the bed, the warmth of the room, the warmth of the night gathered around you, like a mountain valley gathered around a river. Everything is where it should be. Everything is doing what it is meant to do. You are resting, and the mountain is standing, and the weather is moving through the world, and the stars above the summit are very old and very steady and very beautiful, and you don't need to see them to know they are there. Rest now. You are held. The mountain is patient, and the night is long, and tomorrow will arrive in its own time, as it always has, as it always will. Sleep well.